Welcome everyone back to the Berlin Functional Programming Group. This evening, I am pleased to meet and introduce you to Andrew Lelechenko, who is the second person to reach out to me and ask to do a talk, which I really appreciate, and I want him to serve as a role model for everybody attending this meetup and watching this video. Please get in touch with me if you would like to give a talk at our meetup. I am happy to have anyone speak on functional programming topics because this is a small community and we should all be sharing our knowledge and supporting each other as much as possible. Andrew is joining us tonight from London and is going to be speaking about the Enum type class. Well, he says Enum instances on steroids, and we're going to find out what exactly he means by that. And according to the bio he sent me, he has a background in both mathematics and computer science, which I don't imagine he holds in equal esteem, if I know anything about computer scientists and mathematicians. He also has a PhD. And even so, he decided to go into industry. I'm a little jealous of him. I was in a PhD program myself before quitting and going into industry, but I didn't finish mine. But you know, Andrew, maybe you're going to inspire me to finally do that. Except I wasn't studying computer science or mathematics. I was studying English literature and Shakespeare and things like that, and then found my way to Haskell. So, you know, one story can be very strange sometimes, but tonight, not about me, totally about Andrew. I'm very interested to hear what he has to say about a it seems like a very narrowly focused topic, but one that I think he feels we can get a lot of mileage out of in our practical work with Haskell. So I'm looking forward to his talk and his discussion and also your questions. So please think of some good questions and ask them during the talk, and we'll find time for that, and enjoy. Andrew, I'm going to hand it over to you now. One moment, let me just, there you go. So can everybody see Andrew's screen? Did everyone see his slides? Yes, okay, good. So Andrew, the floor is yours.
Hi everyone. I'm gonna give a talk about type class for enumeratable data in Haskell. It's a built-in type class Enum. I'm gonna blame it for its shortcomings and issues, and I'm gonna show you two alternative packages which are aiming to provide basically a better Enum in all aspects. I'm not affiliated with authors of these packages. I do not intend to take any credit in their development. It's just nice packages which I encountered on Hackage, and I want to share them with you. So we'll start with discussion of list generators in Haskell. Haskell provides 4 types of list generators, which are an extremely powerful tool. So the simplest one is how you generate a finite range of numbers or any enumeratable objects. You just type your starting value, your finish value, and you put 2 dots between them, and you immediately get a full list of values, each in between of your bounds. You can also use the similar syntax to produce an infinite list of values starting from a given one. And there are also advanced possibilities to generate ranges of numbers with some step, like you want to generate all odd numbers between 1 and 9, then you write 1, 3, and then ... 9. So it means that you decide that your step is 2, which is the difference between 3 and 1. And you also can use the same syntax for generating infinite lists of numbers which increase with a given step. And this is an extremely powerful syntax, and it's one of the things which are very appealing to people when they start learning Haskell, because together with list comprehension syntax, it makes Haskell very much alike mathematical equations and formulas which is generally estimated as a good in Haskell community, of course. And usually people do not expect any issues, any quirks with this syntax. However, there are some. So once we leave our safe haven of integers and for some reason work with doubles, there are some issues. If you write, if you want to generate a list of doubles between 0 and 3 with the step 1, you can write 0, 1, ... 3, and it will produce a list 0, 1, 2, 3 as expected, both for integers and for doubles. But if you use not 3, but 3.5 as your upper limit, you suddenly will arrive with a list which ends with 4, which is quite unexpected actually, because we think about these list generators as about ranges. And we asked Haskell, we asked GHC to give us a list of doubles between 0 and 3 and 5 with step 1. So yes, it's a bit of a silly request, but we would expect 0, 1, 2, 3, not 4. We do not expect it overflow beyond the upper bound. And it's actually not quite clear to me why. I mean, the short answer is that's because Haskell report says so. So Haskell report has a very specific clause which describes how list generators for doubles work. But it doesn't give any justification, any rationale behind this decision, why ranges for doubles can overflow this way. I have a guess why it's so, because basically it's a choice between two surprising behaviors. One is enshrined in Haskell report, which is that your doubles may grow bigger than your upper limit. And another possible approach is to treat double arithmetic, floating point arithmetic exactly, yeah, and take care about all comparisons in the strict sense. So eliminate any kind of rounding. But in this case, we will end up with equally surprising results if we ask Haskell to return us a range, a list of doubles between 0 and 0.3 with a step of 0.1. It will suddenly, if we disable any rounding, if we do it naively, it will suddenly return us only 3 values without 0.3. And the reason is that floating point arithmetic is quirky, and 0.1 plus 0.1 plus 0.1 is actually larger than 0.3. So if we do not employ any rounding, and if we do not make any discounts for rounding errors, we'll end up with surprising results as well. And so we discussed that we have list generators for integers, we have list generators available for doubles. We actually can have list generators for user-defined types as well. So imagine we define a type to hold a weekday, which is from Monday to Sunday. So this type has 7 constructors without any payload, without any additional arguments, right? And it appears that we can use list generators in the very same way as with integers. So we can just define the range between Tuesday and Friday, and it will give us a list of 4 values. We can even define a range with a step, which probably doesn't make particularly much sense in this scenario, but nevertheless we can. So we can say that we start with Monday and our next tabulation point is on Wednesday and we end on Sunday, and it will give us Monday, Wednesday, Friday, Sunday, which is nice. And it's cool that list generator syntax is not hard coded in GHC. We can use it for our own user-defined data types. And an alert reader and alert viewer might have noticed that I didn't only define data type itself, I also asked GHC to derive Enum type class. And the reason is that actually it's Enum type class who is responsible for list generators, for this syntax to generate ranges of values. What appears actually is that those 4 types of syntax for ranges, they are just a syntactic sugar above simple methods of enum type class, which are enum from, which gives us an infinite list starting from a given value, enum from then, which gives us an infinite list with defined by 2 first values, enum from 2, which gives us a finite list, and enum from then 2, which gives us a finite list with some step between elements. It's actually not the whole story, because enum class has 4 more methods, not only these ones, but it actually starts with defining 2 core methods, 2 core functions of enum type class, which are from enum and to enum. And everything else is defined in terms of these 2 functions. So first of them will take your data and convert it to a corresponding int. And second one will take int and convert it to a value of your data type. So for example, if we have enum instance for days of the week, Monday is converted to 0 and Sunday is converted to 6. And to enum does the opposite conversion. So to enum from 6 is Sunday, to enum from 0 is Monday. And in terms of these 2 functions, enum also defines successor and predecessor functions, which are basically increment and decrement in old plain C language. And the default definitions are basically doing very simple things. They convert your value they map your value onto int, they then increment it, then map value back onto your data type. And pred is doing decrement. These are default definitions, a bit simplified. I have no idea why these 2 functions have such weird names. I can agree with suck, but I don't know why pred is pred. It's so annoying. I always want to use pred for a predicate, and GHC always complains about shadowing names, and I need to either use just p for predicate or write predicate in full as a name of some variable or function. And then we have these functions to generate ranges, enum from to, and internally, again, I'm talking about default definition, and I'm talking about the default definition in very simplified form. They basically take so enum from is aimed to generate an infinite list of values starting from a given one. So what it basically doing, it converts your x to int, then it generates an infinite list of ints starting from this one, and then it map values back onto your data type. And same thing happens with enum from 2. But we just have this cutoff at upper bound. These are very much simplified definitions actually for most of built-in types in Haskell, like int, word, and so on. You have specific better definitions of enum from 2, because it's important to do not allocate anything and to fuse well with other with consumers of your lists. But so these definitions on these slides are not actually what is used in base, but they are functionally the same, at least for the purpose of this talk. So what I want to emphasize here is that basically all these list generators, they boil down to from enum and to enum functions, which convert from between int and your data type. And what is bad here, actually? The bad part of enum type class is that basically there are too many partial functions. So you cannot increment beyond max bound, right? But what would you get? You wouldn't get nothing as in other better designed Haskell functions. You'll get just runtime error. And you cannot decrement beyond min bound of your type again. And this again raises a runtime error, not any kind of maybe value or something. Most of data for which people derive enum instance is small one. So it's some simple enumeration like days of week or month or something else, which is like maybe dozen or couple of dozen elements. And in enum type class, we have function toEnum, which promises us that it takes any int and returns us a value of the type. But it's obviously a lie, because I cannot convert like 100 to a day. And it's again enshrined in Haskell report that toEnum is a partial function, and if its argument is not in the range which is expected, it will raise runtime error and your application will fail with horrible consequences. Other types like integer or natural, these are types for numbers of arbitrary precision, as they are bigger than int. So this function which converts from integer or from natural to int also is not quite well defined. It somehow needs to truncate values, or maybe it has to throw runtime errors if its argument is too big. And in general, strictly speaking, if we have functions which convert, if we have total functions which convert between a and int, it basically means that type A is isomorphic to int. And it means that the only total instance of enum is enum for int, which doesn't make much. You cannot benefit much from this type because it's from enum and toEnum are just ID functions. So the issue here is that enum type does not gives us enough information. Enum type class doesn't give us any idea what range of values is acceptable for toEnum. What range of values is acceptable for decrement and increment? Where is that value which we cannot increment or decrement? And it's a pity because from enum and toEnum functions, they have a lot of utility reaching far beyond this list generator syntax. If you have a way to convert between your data type and int, then you can easily generate random values of your type, right? So you just need a random number generator which gives you int, and then you apply from enum to obtain a random value of your type. You can also have faster maps and sets, because in containers package there are maps and sets for general data types, and there are specific faster versions of int set, which is a set of ints, and int map, which is a map from ints to some values, which are faster because they can use some bit fiddling. They can they know how big how many memory needs to be allocated for keys and so on. So if you have a fast way to convert between your data and int, you can use int map as a substitute for a map from your data type to something. And it could possibly work faster because int map is faster than usual map. Another important application is unboxed vectors. It's very tedious to define unboxed vectors for your data type unless it can be derived somehow. But if you can convert your data to int and back, then you can just convert it to int, store it in an unboxed vector of ints, then read it back and convert it back again and restore your values. So it would be nice to have better from enum and to enum functions in this type class, but unfortunately there are none. And these are very dangerous. Is a common source of errors. Even bigger issue from my point of view is that we, as we discussed above, we can derive enum instance automatically. GHC will derive it for us, but only for types which constructors have no fields, so only constructors with no payload. So for example, imagine that we would like to refactor our type for days of week. We'd like to split it in two types, weekday and weekend. So we can define weekday and derive enum automatically. We can define weekend and derive enum automatically again. But if we try to define day as a sum type, like we work on weekday or play on weekend, and we ask GHC, please derive enum because, well, it's isomorphic to our previous data type, shouldn't make much difference and doesn't look that difficult. But actually GHC will complain and it will refuse to derive an enum instance for day. And also there are no enum instances for built-in types, which are more complex than just simple enumerations. So for example, it sounds reasonable to have enums for maybe or for either. They're like, okay, I want to generate a range from nothing to just true, which contains three values, nothing, just false, and just true. Yeah, but since there is no enum instance, GHC will just refuse to generate a list. And the reason why deriving of enums is so much limited is that basically it's not that easy. If you want to derive an enum for day, so how would our function which convert values of type day to int look like? So if we have constructor work and weekday, then we can convert it to int easily, just using from enum function of the underlying data type weekday, which has its enum instance. But if we have, for example, play Sunday, and we want to convert it to some int value, we don't really know. We would like to convert it to 6, but to do this, we need to know how many values were in weekday. So we need to know that there are 5 weekdays, and we are working with play Sunday. Sunday is the second element of weekend, and we need to add 5 plus 2. Well, we have our indices start from 0, so we end up with 6. But enum instance does not give us information about how many elements, how many values inhabit this weekday type. So we need somehow either hard code this information or have some other workaround. It's not that easy to define enum instance in its current avatar. So we would like to tackle these issues, and basically both of them are about cardinality of our data. In both cases, we were talking about how many elements inhabit our type, what are the range, what values, what is the range of from enum and to enum conversions. So there is a technical mathematical term, cardinality, which is just a fancy word for how many values inhabit a type. So for example, cardinality of bool is 2 because there are only true and false. Cardinality of unit type is 1 because there are only one inhabitant. And there is also a funny type of void, which has 0 inhabitants at all. And we can easily count cardinality of more complex algebraic data types. So imagine that we have a data type foo with 2 constructors, foo and bar, and foo constructor has 2 fields, both of which are bool, and bar has only 1 field, which is unit. So how many values do inhabit this data type? It's 5 of them, right? Because it's either 2 times 2 values with foo constructor, and there is 1 value with bar constructor for the unit. So in total, it's 5 of them. And so we would like to, let's try and make a draft of a better enum type, which will communicate with users not only how to convert from your data to int and back, but also what range of ints is acceptable. So we basically define our class myEnum, which has to myEnum and from myEnum functions, which are similar to enum and from enum in normal enum type class. But it also has a function cardinality, which takes an argument. As an argument, it takes a proxy value of your type. It's not used, it's only for the sake that GHC is able to dispatch on a correct instance of your class, and it returns an integer which says how many values inhabit A. And it's all nice and good, but really, do we want to write several hundred of myEnum instances by hand? Like, doesn't look like an interesting task. We would like somehow to make GHC to derive our type class for us automatically. And each time when we want to derive some type class automatically, which is not a built-in derivable type class in GHC, we usually resort to using generic representations. So what it's all about? Algebraic data types, which is just your normal data types in Haskell, are always isomorphic to a sum of products of some types, which is called its generic representation. It's basically called algebraic just for these particular reasons, that it's algebraic in the sense that it's a sum of products. So for example, if we have a data type foo, which has one constructor foo and two fields, bool and bool, it's obviously isomorphic to a tuple of two bools. Isomorphic means that we have direct one-to-one correspondence between these types, between foo and tuple of two bools. Or I'd write it in another notation. I'll write it as bool times bool, basically. And if we have another data type which has two constructors with payloads, so first constructor is bar and its payload is a value of type bar, and second constructor is bus and its payload is a value of type bus. Yes, and it's isomorphic to either bar or bus, or in another notation, it's basically a sum of types. One more example, if we have a type with just one constructor and no payload, it's isomorphic to unit. There is only one value of this type. And in more complex cases, as we discussed above, if our type has two constructors and first one accepts two fields of bool as its payload, it's isomorphic to either tuple of bools or unit, or another notation, it's isomorphic to a product of bool times bool plus unit. So, and every ADT, every Haskell algebraic data type is isomorphic to the sum of products. And a good thing about this, why it's important at all, is that GHC has an automatic way to convert between types and their generic representations as sum of products. And it's very useful because it allows us to explain to GHC how to derive instances of our user-defined type class, how to define them. It's enough to define them on sums and products, and then GHC will figure out itself how to define your type class for your user-defined data automatically without writing instance manually. So I'll skip some plumbing and some boilerplate, but basically the idea is that for our user-facing type class myEnum, we need to write a shadow counterpart, which is gmyEnum, and all its functions have this prefix g cardinality to g from g. And we basically need to define this type class for sums and products. So let's start with sums. If we encounter a sum of types A and B, and both constituents, both A and B, are myEnum, so they have these functions defined for them, we can easily define cardinality of the sum of types. Cardinality of sum of types is just sum of cardinalities, right? So either AB has how many inhabitants are in either IAB. It's how many inhabitants, it's a number of inhabitants in A and number of inhabitants in B. Then we can define functions which will convert integers to data. Basically, it's easy. We just check how many values inhabit our left data type A. And if we are asked to convert a number which is smaller than cardinality of A, then we just generate the value of type A, and L1 is basically left of either. And we generate the value of some type. or if we are asked to return a value for n which is greater than cardinality of first summoned in this sum type, then we just subtract cardinality of A, generate a value of type B, and wrap it in right. And we can define a conversion in another direction, which will take a value of our type and will return us an integer. So if it's left x, then we just use underlying gmy_enum instance to get its number, its position in a list of values. And if it's right x, then we take position of x in gmy_enum b and offset it by cardinality of A. And in the same way, we can define a generic instance for products. So again, cardinality of product type is product of cardinalities of its components. And if we want to generate a value of a product type by its number, you can imagine that our product type is basically a rectangular area with two coordinates, Q and R, and Q corresponds to type A and R corresponds to type B. So we can just take quotient and remainder of N divided by cardinality of B. So quotient is basically how many, is basically our Y is our A coordinate and remainder is our B coordinate. And the other way around, we can take a value of product type and generate an integer to which it corresponds. And one can check that that the composition of from gmy_enum and to gmy_enum is actually identity, because we do the same thing. We basically represent our product type as a rectangular area. So, as I mentioned, I skipped some plumbing and some boilerplate. Anyone who is interested to look in all nitty-gritty details can look at this link below. So once this tedious work is done, once we defined our data type for sums and products, everything else actually works like a charm. So for example, we can define we can write down a new data type action, which has 3 constructors, and these constructors have various payloads like units, bools, or maybe 2 bools. And then we just spell some magic words, which is please derive generic and please derive my enum. Please, dear GSC, you're very clever. Please do it yourself. I do not even want to bother about it. And GSC actually is very much capable to do it once we defined my enum for sums and products. And we can test this thing in GSCI. So we can ask, what is the cardinality of action? How many different actions there are? And it's 7. Which is more or less expected. And we can also ask GHC to list all possible actions. So we generate integers from 0 to 7-1, and we apply to my enum to them, and we have our nice and shiny list of all possible 7 actions. And we didn't write a line of instances for action ourselves. This kind of magic. So this part of the talk, it deals with the issue that enum couldn't be derived for anything which is more complex than just a list of constructors without any payload. In this part of our talk, we defined a myEnum type class, and we defined generic instance, and we write some generic stuff for it so that GHC actually can do its job properly. And the reason why it can do, why it can derive instance and why it works nicely is that we augmented enum with cardinality of our data. This is a key component. However, this is still not quite satisfactory, because we mentioned above that another issue with enum was that we actually can easily make a mistake. For example, if I do not subtract 1 here, if I just ask to myEnum on 7, I'll still get some kind of runtime error. I mean, it's better than just vanilla enum, because at least I can ask about cardinality of my data, but I can still do a stupid mistake. I can still do some off by 1 error here. How can we safeguard ourselves from these kind of mistakes? And so we would like to make legal states unrepresentable. It's a usual mantra of Haskell. So at the moment we have our type class myEnum, and it has these 3 functions. And again, to myEnum and from myEnum, they technically accept any integer, and thus they are inevitably partial, which is not cool. We don't like it. It appears that modern GHC provides us with enough dependent types stuff to work around this nicely and without much runtime overhead. It appears that in modern Haskell, in modern GHC, we can define data finite with n of kind not. Kind not is for type level numbers, which has exactly n inhabitants between 0 and n-1. So we can define this data finite with the number of inhabitants on type level. This is a type level number, not term level one. And then what is left to do is to promote cardinality function to the type level. So previously cardinality was a function. It took a proxy to explain it what type A we are talking about, and it returned a term level number. What we can do, we can, instead of function, we can define type family cardinality, which will again take our type A, and it will return net, a type level, not a term level, but type level number. And then we can use this type level number to define correct total to myEnum and from myEnum functions. So that to myEnum says, I take finite of what size? Oh, finite of cardinality of A. And you wouldn't be able to construct a wrong value because the definition is because of definition of data type finite. And other way around, from myEnum says, okay, I return you an integer, but I promise you it's not every other integer. This is an integer between 0 and cardinality of A-1. And this way you can augment this myEnum with decrement and increment, which is type safe. And it's actually, the thing is that type level naturals are built in GHC, so they have quite good performance. So this solution does not have any tremendous overhead in comparison to the simpler one. So this approach can be found full-fledged in all its beauty in two packages, finitary and finitary derive. So in finitary, you will find basically a type class similar to my Enum, a bit different, but the idea is the same. And finitary derive is a supplementary package which defines a type, which defines unboxed vectors for enumeratable types automatically for you, which is very helpful. And it's something which is much better than trying to derive unboxed vector yourself. So this slide was about making our construction more type safe. This is one direction in which we can go from our initial my_num type class. Another direction is to cover more types. So at the moment, we work only for for finite types, which have finite number of inhabitants. But it would be nice to have some way to enumerate more complex data. For example, some data which has infinite number of values, infinite but still small. And when I'm saying infinite by small, I mean countable. Technically, in set theory, a data type is called countable if it's isomorphic to integer. So you can write total functions from your data to integer and a total function from integer to your data. So this type inevitably has an infinite cardinality, but it's still small in some sense. It's not as big as, for example, a set of real numbers, which is much bigger. So what is interesting about countable types? It's a bit counterintuitive, but sum of two countable types is also countable. So if you have either integer, you can it's still isomorphic to just integer, even while it looks like it's twice as big in inhabitants. The reason why is that you can map left elements, you can map integers with a left constructor to even numbers and integers with right constructor to odd numbers. So this is give us first part of our conversion from either integer to integer. And you can go back, right? So if you have some integer, you can check, is it even or odd? And if it's even, then you know that you have to return left and n divided by 2. And if it's odd, then you can return right and n-1 divided by 2. So sum of countable types is countable. Even more interesting is that product of countable types is also countable. So if you want to build a conversion from pairs of integer to integer and back, you can just take bit representation of these numbers and you can just interleave them. So you take bits from the first component and put them at even positions in your result, and you take bits from your second component of your tuple. In our case, it's all zeros, and you put them on odd positions in result. And you can go back again. So you have integer, you can filter out bits on odd positions and filter out bits on even positions and restore your pair of integers. So far, so good. So at this point, what we see is that sums of countable types are countable and products of countable types are countable. It looks like we can use our approach with generic once again. But what is uncountable then? It looks, at the moment, it looks like everything in the universe is countable. It appears that set of functions, for example, set of functions from integer to bool is very large. It's uncountable. You cannot build a isomorphism between set of these functions and just integers. But you can build an isomorphism between functions from integer to bool and set of real numbers, basically because you can, because the function from integer to, because this is basically an infinite list of zeros and ones, and infinite lists of zeros and ones have one-to-one correspondence to real numbers, basically. Another interesting question is here, is there anything between countable and is there anything in between sets which are isomorphic to integer and sets which are isomorphic to real numbers, which is the famous continuum problem. And its resolution is that we cannot prove neither of these. We cannot prove neither that there is something or there is nothing in between. We shall take it as an axiom, but I got digressed into set theory. Sorry for this. So we discussed that for countable types, products and sums are still countable, and we can employ our trick with generic instances, which allows us to extend our myEnum to cover integers and types which components are integers or other infinite but countable types in this framework, so that we have cardinality, which in this case is either finite value or just we say it's infinite but countable, and we have nicely defined functions from cardinality to A and back. And for example, this makes, for example, list of bool is actually a list of, assuming that it's a finite list. Yeah, so these lists form a countable set and we can treat them as enum on steroids. This approach, which takes into account infinite but small types, is implemented in another package which is called Cantor pairing. It's because of Cantor is surname of a famous mathematician. And it would be interesting to actually combine these two extensions. So we have our basic myEnum, and we discussed two extensions. First extension was to make it more type safe, so that to myEnum and from myEnum are total functions. And the second extension was to cover for infinite data types. But it seems that in current Haskell, because of some technical difficulties, it's difficult to combine these extensions under the same framework. So we'll end up having different packages. And that's it from my side. Thank you. Am I alone here?
Hi, hello. Yeah, sorry, there was some noise coming from somebody. I muted them. So are there any questions? So let me know in the chat if you have a question. You don't have to type your whole question, actually. We can just let you ask. You're getting some nice comments. Uli, do you have a question? Do you want to ask yourself?
Yep. Sure, I can do that. Hi, thanks for the talk and yeah, this very interesting and also very easy to follow explanation. That was really cool. Yeah, I'm wondering how this compares to the more or broader concept of refinement types, where you have a general type and then you limit it to, for example, have a string that only has a certain length or an array that has only a certain length or these kind of things. And seems like there's also libraries out there which are so-so to work with, but there seems to be a discussion.
Do you mean that we can use refinement types to work around our partial functions to enum and from enum?
Yeah, exactly. To what you've shown, it feels like it's also some sort of refinement type. And if you can express one with the other, or is this basically solving the same problem?
Well, I think that liquid Haskell would be probably able to derive annotations with refinement types here. Should be not that difficult for it. But I prefer to use refinement types, at least as long as they are kind of liquid Haskell is not yet part of GHC and is not part of standard Haskell, right? So I prefer to use type level numbers and strings as much as possible because this is built in GHC. So this problem is easy enough to use just this finite n data type, which just has a meaning that this is type with exactly n inhabitants. In more complex problems, we may be interested to rely on some liquid Haskell features. Another thing that we actually need not only like proof that our functions are correct, we also need to have an access to this information, to this cardinality. So liquid Haskell doesn't give us a way to, even if liquid Haskell proved some refinement annotation, we cannot look onto this annotation in our code in term level because it's a separate, basically compiler, which is not wired in GHC.
Okay, thanks. Yeah.
Okay, thank you. I just have a question. I don't recall, are you using Haskell in production at work right now? Are you writing Haskell at work?
Yeah, we have a team at Barclays.
Okay, so are any of these concepts things you take advantage of in your day-to-day coding? Are there practical applications you can think of?
Well, of practical applications, there is a pull request into random library, which basically is what I was talking about, how to generate random numbers of user-defined types without any manual conversions. So this is an easy application of this material. And obviously this approach with generics is pretty much universal. You can apply it to make GHC derive instances for your user-defined classes, for other classes as well, as long as you can define it for products and sums and we use it.
Okay, thank you. I don't see any other questions in the chat. So I'm just going to thank you again, Andrew, for the talk this evening. And I want to, since you have this final slide up, I want to recommend everyone have a look at your GitHub account, not just the talks, but some of your libraries. You actually have some very interesting stuff there that I think It's actually very cleanly written, and I think people would benefit from looking at those libraries. I had a look myself. And you're getting some final thank yous in the chat. And thank you from me as well. Thanks for reaching out. Thanks for offering to do this. And come back again if you have any other ideas you want to discuss.
Thanks for providing this possibility.
Yeah, my only regret is we can't do the after meetup drinks, but maybe in person someday you'll come visit Berlin.
Absolutely.
Okay, so take care and thanks again. Have a good night, everybody.
And you, thanks everyone for attending.